topic of this video is mass spectroscopy and isotopes. So hopefully by the end of this video you will understand the 4 parts of a mass spectrometer. You'll know what they are, what they do and how they do it, and to be able to interpret mass spectra to calculate relative masses. So you'll be given some data and you need to be able to use that data to calculate the relative mass of what they're asking you. So here's my crude drawing of a mass spectrometer. As you can tell, I was never very good at art. And there are 4 parts to this, and I'm going to take you through each one step by step. So the first thing that happens to a sample when you put it in a mass spectrometer is that it is vaporised, and you don't really need to talk about the vaporisation step. You'll assume that it goes in as a gas. The next bit is that it gets ionised, and it does this by firing a stream of electrons at the sample, and these electrons will knock off an electron from the sample itself, therefore ionising it. And we say that this is called an electron gun. The next part is acceleration. So there's a bit of the mass spectrometer that accelerates the ions to a speed, and this is done with negatively charged plates. So if an electron has been knocked off the sample at ionisation, it will now be positively charged, so it will be dragged towards the negatively charged plates and slingshotted through it, if you like. This next part here is where the sample gets deflected, so deflection happens next, and that's done with an electromagnet, which can be turned up or down. If you've got heavier ions, ones with higher mass, then you'll need a stronger magnetic field to deflect it around the corner. And then at the end we've got a detector, so detection is last, and that is basically a plate of metal, and as the ion hits it, it will take an electron away from the metal and therefore induce a current in the metal, and the size of the current is directly proportional to the number of ions that are hitting it. So if we just look at the path of the sample again, it will get vaporised at the very beginning, which you don't need to talk about. It will then get ionised with an electron gun. It then is now positively charged, so it will get dragged towards negatively charged plates and it will slingshot through, and it will keep on going straight if it wasn't for the magnetic field here, which will then make it curve round the mass spectrometer. As I said, if it's a lighter ion, it won't need as strong an electromagnetic field as a heavier ion, and then as it's slingshot round, it will then hit the detector at the end, which will measure how many ions are hitting it. So to summarise those 4 main parts, you've got ionisation with an electron gun. You've then got acceleration, with negatively charged plates. You've then got deflection, with an electromagnet, which can be turned up or down. So it can be made stronger or weaker. And then you've got detection, and you'd say current produced is proportional to the number of ions hitting it, or the abundance, which is what you would see, the word you would see in a graph made by the mass spectrometer. So now I'm going to work through an example of how to work out the relative mass of a sample using the data that will be given to you. It will either be given to you in a table or in a graph form, and here you can see that it's being given to us in a graph form. The 2 axes show the relative abundance, so how much of each mass there is in the sample relative to each other. So there's no unit for that, for those numbers. And the mass to charge ratio, which if you're not sure what that is, you can come and see me and I'll explain to you that in a bit more detail. So to work out the relative mass of a sample using a graph, you're basically working out the average of the masses that were detected in the sample you put through the mass spectrometer. So basically I'm going to do a bit of maths using the numbers on this graph. So the first thing you've got to do is work out what the relative abundance is for each of the masses in the sample. So you're just going to read off the graph. So for 90 it's 9, for 91 it's 2, for 92 it's 3, and for 94 it's also 3. And what you're going to do with those numbers, you're going to multiply them together. So you're going to multiply the mass by its relative abundance. So it's going to be 90 times 9, which equals 810. It's going to be 91 times 2, which equals 182. It's going to be 92 times 3, which equals 276. And it's going to be 94 times 3 as well, which equals 282. Notice we missed out 93 because that has a relative abundance of 0, so there's no point putting that in our calculation. The next step is to add up the numbers that you've worked out from your multiplications. And once you've done that, you'll find that 810 added to 182, added to 276, added to 282 equals 1,550. You also need to add up the relative abundances that you multiplied by. So 9 plus 2 plus 3 plus 3. And that adds up to 17. The last step is to divide the number that you got from adding up all of the multiplications by the addition of all the relative abundances. So finally, to work out the relative mass of this sample, you're going to do 1,550 divided by 17, and that gives us an answer of 91.2. Now notice that this final answer, this number here, is between the masses that are in the sample. It's a number that is between 90 and 94. If you end up with a number that's outside the bottom and the top number, then you know you must be wrong, because if you're working out an average of these numbers, then it must be between the bottom and the top number for it to work. And you can see that 91.2 is. So that is a sensible answer from this calculation. Now you can try a couple yourself from the book of questions that I gave you at the beginning of term.